Okay, if not to recap what we covered yesterday, we're looking at the problem of having to calculate the substantial derivative of quantity which is expressed as an integral over the volume of some scalar function f. So this is the problem, because this is now over the spatial region occupied by the fluid at time t. We have to take the substantial derivative. We have to transform this integral to 1 over the reference configuration, which becomes fixed for the body as a whole. Because the substantial derivative means we are going to treat this region occupied by the fluid at volume t, the collection of fluid points in that region, as the body. We have to follow the body in motion to calculate the rate of change of this quantity. So that is the meaning. So then we get f, which is to be expressed as a function of psi and t. Then we will get, in which case we can take the time derivative inside the integral, because it's a fixed region for the body, which can be, we can keep mapping back to this configuration. So we get df by dt times k plus f dk by dt dv naught. And then we showed, so this is over v naught, we showed that this would be df by dt j plus f j times the divergence of the velocity vector v. So now we can bring the j outside. And now we will transform back to the spatial domain at time t. So which then becomes, this is again over v naught, and then we can write this as over v. So this is df by dt. This whole quantity is the capital F. So we're looking at that. So it can be written now as df by dt. Now using the earlier derived formula for the substantial derivative of a scalar function, df by dt plus so that is this quantity that I've written. On top of it we have also a f, and the whole thing is now over the volume V occupied by the fluid at time t. So, back to the integral over the spatial domain. So it can now be written as df by dt times dt plus, without proof, I showed that this group of quantities can be written as the divergence of the scalar f times t. Quite easy to prove that, which this integral now can be written as we have to connect it with the earlier substantial derivative, simply a scalar function, not an integral, which is given by the spatial derivative of the scalar function plus we had an extra term. So for the integral, we again have the spatial derivative plus an extra term which can be expressed as a divergence of f times the velocity dv. Further, using the divergence theorem, I can show, which again I haven't quite proved. This can now be written as an area integral, and this area is the surface. The integral is over the surface that is enclosing the volume in space at time t. So this is what we have. So I can write this as d by dt integral f substantial derivative spatial is an additional quantity. Now, if I look at this quantity, there is an important physical interpretation for this quantity. So what this says is the substantial derivative of the integral is the spatial derivative plus this quantity, which I now want to look at physically what it represents. Because if we now look at the units of the function f, the scalar function f, the lowercase f. Right? So, if I now look at the units, what are the units of this with respect to the units of capital F? The units of f, units of, and by volume, per unit volume. So whatever the quantity, we have not committed ourselves to a particular quantity f and capital. We give many examples of this because it's kind of easily repeated. Whatever it is, clearly the units of the lowercase f is simply the units of the capital F per volume. That is very clear. So now what are the units of f times b? This now becomes a vector because I started with f being a scalar. So when I multiply a scalar by a vector, I get a vector. So these are, but I know you're only looking at the units. So this would be the units of f per volume times distance by time. The units of distance by time and the units of the. This is now a vector. It's a vector which has this units. So if I now cancel this, I now get the units of capital F per unit area per unit time. So what can you say about it? Represents clearly the flux of F. Right? The flux of F, because it is F per unit area per time, and it is a vector. So Fp can be regarded as a flux vector associated with the quantity capital F. Now if I take the units of what would this be? Would it be the same as the units of f times b, or would it be different? It's the same because n doesn't have any units. It's only unit normal. Right? Unit normal doesn't have any units. Right? So it is also flux of f. This is now a scalar. So when I get Fb dotted with n, I get a scalar flux of f, right, associated with the function, the quantity f, capital F. It's the flux of f. Once I have a vector, take a dot product with respect to n, I get a flux again, it has the same units as the flux. It is now a scalar. That is now to be integrated over the area. So if I am now focusing at a particular instant time, where I have a body fluid which occupies a volume B, and this is the area over which I have to integrate. This whole quantity can be regarded, because n is a unit normal outward, so at every point I have the unit normal, and Fb could be not necessarily the same direction as n, in some other direction. Depends obviously on the velocity vector at that point. So when I take the dot product of the two, so I get Fb dotted with n. That is to be regarded as a net outgoing flux of the quantity capital F. Right? So we can write this as the net. So when I integrate this, so this is the flux. When I integrate it, I get this can be regarded as a net efflux, EF, rather than the influx. Efflux keeps going out. Net efflux of air out of the volume V across the area. So I can regard the quantity FV dotted with NdA, the integral, the whole quantity. We get a flux, then we get a scalar, then we have to integrate it, we get the quantities. So this can be regarded as the net. So the substantial derivative of quantity, the integral of some scalar function f can be regarded as a spatial derivative of that quantity plus the net efflux of the quantity capital F out of the volume across the area. This is somewhat like an accumulation term, but this would be like turn out to be an outgoing term. Now we can easily give an example. Suppose let's say we take F is equal to the density. The mass density. Now clearly, if I take F, what would then F be? It's the mass of the fluid inside the volume. So F is here, M. So now, if I look at this term, rho V dotted with N. So what would that do? So I now write d by dt of integral rho dv is equal to, this is the famous mass balance for a controlled volume. It will turn out, I mean, we can regard it like that, you see that later. Plus, the derivative of change of mass, substantial derivative, is equal to the time rate of change of mass within the volume of fluid, the spatial derivative, plus the net efflux of mass. This is actually a rate because this is dividing by time, net efflux rate. All of these are rates. Out of D. So this is what we are getting. So now I will briefly explain, complete the proof of these two. I am not going to prove the divergence theorem, but I will just prove this. How do we go about proving that this is equal to this? This will give you an idea of how to go about proving any identity. It could be a scalar identity, it could be a vector identity, it could be a tensor identity. So first you have to identify when an identity is given to you, for instance in an assignment or an exam. First you have to identify whether it's a scalar or a vector or a tensor. Obviously all the terms in that equation must be of the same quality. You cannot have a vector equal to some tensor. That is absurd, right? So now let us take up the proof of this. This is very easy to prove. So what I want to prove is this is what I have assumed here. I have to prove it. The easiest thing is we can start from any side, left hand side or right hand side. First is identify that this is clearly a scalar equation. The divergence of a vector is a scalar. This is a divergence of a vector is a scalar multiplied by a scalar. That's also a scalar. This is the dot product of two vectors. One is the velocity and one is the gradient of the scalar function. Yeah, that's also a scalar. It's a scalar identity. Identity means they're equal. So we want to prove this. Best is to identify the operation, and you should. I will list out a set of operations that you should remember for the purpose of this course. Right? Certainly, divergence of a vector field, the formula you should know. what it is. So we've already given that. Summation index will be assumed. So I'm not going to write the sum, so you have to get used to using the repeated index summation convention. It can also be written in an even more compact form like this. So I have to take this. First I use this. I prefer using that because it's simpler. So now all I have to do is to identify what the A is. A is clearly f times b. So this is equal to d times d by dxi of the ith component of A. So the ith component of f times b is simply f vi. That's all there is to it. Now I see that this is clearly a derivative of a product. We know how to calculate the derivative, and you are having two terms. So clearly it's very easy to identify the two terms. So this can now be written as f. The summation convention is taken care of automatically. So you don't have to worry about whether this is this. We are just suppressing the sum I equal to 1 to 3. That's all. Right? So it is there. Back. So you don't have to worry about it. You just differentiate it as if this is just a regular differentiation. Vi df by dxi. Clearly, this is f times the dpi by dxi. If the summation includes sign convention included, dp1 by dx1 plus dp2 by dx2 plus dp3 by dx3. So that is the divergence of the velocity vector field. This is b1 df by dx1 plus b2 df by dx2 plus b3 df by dx3. That's nothing but this is something that is quite easy to do. We could have also proceeded from the right hand side and gone back and proved that it is equal to the left hand side. Or sometimes it might be convenient to go halfway, to proceed from the right hand side for both the quantities and mean in between. It entirely depends on the situation. Right? But so this is what we have. Now regarding the divergence theorem, I will give you a very generalized form of the divergence theorem that I found in that article by Serrin. Divergence theorem basically converts the volume integral into an area integral and vice versa. You have an area integral, you can convert it to a volume integral. That is found a very convenient way of expressing it, and that is found in the article by Serrin that is given as one of the references. So, this is how he states this integral some scalar function, let's take f comma I. This is actually df by dxi. dv is equal to f ni dA. Very simple. F can also contain the index I. It can contain other indexes also. It depends on the situation. We now see how this one formula is sufficient for us to convert back from area to volume integral without worrying about whether it is converting a divergence to a dot product with respect to n, or we would encounter other cases, more complicated cases where this can be applied. And so this can also be written as df by dxi, but I am not now move to comma. So all I have to do is, when I encounter a situation, I have to identify the quantity f. Unfortunately, we probably will make this on g. We have a, it doesn't really matter. We already have an f here. So the general problem is to make some g, which is obviously a function of x and t, that is the spatial coordinate, because comma I means derivative with respect to the spatial coordinate xi. Let us now see, I have now this integral integrand is, because the integrand, once you identify, if you are able to express it in this form, then you identify the function g, and on the right hand side I simply blindly put g multiplied by ni and integrate over the area. So let us now see what this is. This is the divergence of the combined product of f times b, so that would be f bi comma I dt. If you want, you can write the d by dx side, to shift to this. So now, what is g? G, what is the function g? F times bi, that's all. So you separate out the dot I, comma I rather, and look at what g is. So g is clearly f times bi in this case. So now that is clearly equal to f bi ni dA, that's all. So the g just comes there. You can very clearly see that this is nothing but fb dotted with n dA, and we get the well-known form of the divergence theorem. There are many other instances where this would become more, each time we don't have to see what is the corresponding divergence theorem. There are many versions of the divergence theorem or the Gauss's theorem or whatever name is associated with it. All of those can be combined into this one formula. If you know how to apply this formula, you can use it back and forth whenever it's needed. We see more examples of that. Now we will take up this, and this can also be written, if I use the first formula, this one, this can also be written equivalently as a volume integral. Both forms will be useful as we will see. So now, what is the quantity d by dt of rho dV? So we are now focusing on a particular region at time t occupying a volume v. So I have to follow this body in motion. I have to calculate the time rate of change of mass of the body. So what is that? It is 0, because we have said the body moves from one configuration to another, so it will have different, the material points inside the body will have different location, they have different velocities and different accelerations and different momentum as we go along. But one thing that remains fixed is that the body is a collection of material points with fixed mass. So as the body now moves to a different configuration at, let's say, t plus delta t, whatever else might change, the mass is equal to the mass at t plus delta t. Mass at time t is the same. So the time rate of change of mass of the body as a whole is 0. So this is now equal to 0. This will now lead to the famous continuity equation. So this is 0. So I have two terms on the right hand side. So the sum of those two terms are 0. So what I can do now is I can take, we have seen that this is a spatial derivative, so I can take it inside and out of the integral. So I can now write this as integral dO by dt. I'm now going to combine the two because they are both over the same volume V. One has dO by dt, another has the divergence of rho times B. So I can write this as from this I will conclude that the integrand itself is same. Normal normally when an integral is zero, it doesn't mean that the integrand has to be zero. But here I will conclude that typical procedure that we will use repeatedly. What we are doing is, since the choice of the body is arbitrary, what I am trying to point out that if you look at this is the famous continuity equation. It's a local equation. This is like a global balance that has led to a local equation which is valid at every point in the fluid. After that is what it is. This is a quantity that is valid at each and every point and at every instant of time. Whereas this is for the body as a whole. This is for each and every point. That's what is called as the local equation. So suppose I want to establish a local equation at a particular instant of time, and let us say at a particular location x. So now, what I can do is, I can choose, since the choice of the collection of variable points is arbitrary, I can choose, let's say, first this region, which I have marked here as the body of interest. And clearly, this integral will be zero. Now, I can choose a smaller region in space as now the collection of material points. That is entirely arbitrary. And again, for that mass of fluid also the mass is conserved. Now the body has changed. It is a different body that I am considering. It is zero, but around, I am choosing that body around the same location, x, at which I want to establish a local equation. So I can keep on doing it. So as I shrink the size of the body progressively at all stages without any discontinuity, I am getting that the integral is zero. So I will argue that in the limit, as I go to smaller and smaller regions in space as the body of interest, continuing to get the integral to be zero. I will argue that because in the limit, then the integrand itself has to be zero. As I now collapse to the point, in the limit I can argue. This is a limiting argument. Right? So it might not be very precise explanation, but this is certainly valid. In the limit I can prove that as I shrink the volume around the point which I am going to consider as a body of interest and proving that the integral is zero at all stages, in the final limiting case I will argue that the integrand itself has to then be zero. This is what is called a continuity equation. Now this is a very standard procedure that making a argument on this is basically the principle of conservation of mass. To make a statement on the property of a body. Property of a body is its mass is conserved. So from that we are collapsing to a point within the body and then concluding that the quantity dO by dt plus the divergence of rho times d is valid at all points within the fluid. This is a standard procedure. Global balance we get to a local equation. Now, another standard procedure would be I would just integrate the local equation now over any suitable control volume that is of interest to me. Let's say I have a pipe through which fluid is flowing, or it could be a reactor, a CSPR, whatever. It could be anything. Right? So, but typically reactor will have a mixture. So here we have only particular single component fluid. That might not be a good example. You simply have a tube through which water or something is flowing. So now I can integrate, since I have now got an equation that is valid at every point, I can integrate it over any control volume of interest. So from the local equation, I can integrate it over a fixed, I'll assume the control volume is not moving for simplicity. Equal to that will also be 0. 0 when it is integrated over any volume will be 0. So I am getting now a different kind of a global balance which is valid for a control volume for which the mass need not be conserved. So for instance, I can have fluid flowing, let's say. This is the control volume of interest, the pipe, a particular region in space. So we are now following what is happening within this region. So now I can write this as d by dt, take the spatial derivative out, and I can write it as minus which is of course equal to, I can leave it like this, but I get a better physical interpretation than I write it like this. So now this is clearly nothing but this is after all the mass of fluid within the control volume at any instant of time, because I have integrated over the entire control volume, so this becomes now a function of time. So I can write this now the traditional way. I have a partial sign here. This is effectively dm by dt. This can be written, since rho v dot nda we have clearly seen is the net rate of efflux or outgoing flux. The integral of that will be the net rate of mass flowing out of the control volume. Clearly, the negative of that is the net rate of mass into the control volume. So this is clearly the rate of accumulation of mass and this is standard. This is the net rate in. I can write it as mass rate in minus mass rate out. So typically you have an inlet and you have an outlet, or many inlets and many outlets, or whatever combination. So I can write it as, this is the famous rate of accumulation of any quantity is here, no other quantity, it's just the rate of accumulation of mass within the control volume is the net rate of mass into the control volume minus the net rate of mass out of the control volume. In fact, we have already got that. We could have seen that from here itself. Here itself, since this is also equal to 0, I already have that. This is a typical, this is the first derivation, we got the equation, but typical procedure which we will adopt is a law of state on the body to a local equation to the control volume equation. This is standard procedure. So we make a statement on the laws applied to the body. The first statement is the principle of conservation of mass. From that, the standard procedure is to get a local equation which is valid at all points within the fluid. And from that, we integrate over a fixed control volume to get the control volume equations that are very common in the chemical engineering literature. Are there any questions about these equations, the formula that we have derived, the divergence theorem and the principle of conservation of mass and the various forms of the principle of conservation of mass? Yes.
So the divergence of that that is like mass in minus mass in.
So when you write it in this form, it becomes clear. It's not quite clear here.
If we represent it via the Gauss divergence theorem, you are telling that it is fx that goes out. So mass in minus mass out, that is accumulation. That accumulation term is going out.
No, the accumulation term is not. Accumulation term is different. This is the accumulation term. The two terms are different. The principle of conservation of mass says that they have to be equal. The nature of those two terms are different.
Here, then what is the physical significance of writing?
Writing it like this, that's what, it's not very clear because everything is a volume term. But when you write it like this, its meaning becomes clear. You can leave it like that. When you write it in different forms, the equation have different, some have easier physical interpretation. We all know the rate of change of mass within the control volume, that is the rate of accumulation of mass, is equal to the net rate of in minus out. So when you look at this, for instance, right, it's not very easy to see that this actually represents the net rate of mass in the divergence, because it is something that is over the volume. When you write it like this, you get this interpretation. Mathematically, the two are equal. When you write it as an area interpretation, you get a somewhat more revealing physical interpretation.
Sir, what is the significance of that minus sign to the right side?
Yeah, the minus sign is coming because I'm taking this to the other side. So this n is always towards an outward normal. This integral alone represents the net rate of mass out of the control volume. So when you put the negative of that, you get the net rate of mass in. Because by convention we have chosen n to be the outward normal. So when you calculate rho v dot n, we get the mass flux out of a particular location on the control volume, let's say, on the control surface, where it is exiting or incoming. And then you look at the normal, outward normal. So rho v dot n, that is only at one point. Because mass, flux, even though it has a vector rho times v, mass is effectively a scalar. So to get a scalar, what I do is I take the dot product to the outward normal. So that effectively gives the mass fx, flux, at a particular location. So when I integrate it over the entire control area, or the area enclosing the control volume, then I get the net mass rate Fx. When I take the negative of that, I get the net mass rate influx. So you get the very well-known formula, rate of accumulation of mass is the net rate of in minus net rate of mass out. Are there any other questions? If not, we'll move now to the next stage, and that is the Newton's law, or the Euler's law, whichever name you want to call it. It is now the rate of change of statement of it is rather the momentum balance. But principle of conservation of mass, what we are now going to look at is the balance of momentum. We can call this Euler's law of the balance of momentum, which has as its inspiration the Newton's second law, which says the net force acting on a body is equal to the time rate of change of momentum rather than net force acting equal to mass times acceleration. Right? We use the other interpretation of Newton's second law. So the rate of change of momentum is now represented. Now again, this will be a statement on the body, because we have said that the laws of mass point mechanics carry over to the laws of continuum mechanics. When they are applied to the body, it's very natural. When there, the rate of change of momentum is equal to the net force. Here also it will be the same. This is the momentum of again I can focus the particular time t. This occupies the volume V. Now when I put d by dt, so I can calculate a momentum associated with this region of fluid that is given by the interval. So I am not saying now whether this is a body in motion or not. There is no my choice that I have to make. So when I introduce a substantial derivative, immediately it means that I am now choosing this fluid collection of points, fluid points in the region V at time t as now the body of interest. So now I have to follow this body in motion. I am looking at the time rate of change of momentum of this body. That is the meaning of this. And what the Euler's law of balance of momentum says that this is now equal to the net force acting on the body. So the net force, as we have already seen in the initial lectures, is composed of two parts in continuum mechanics. One is the body force, which has a representation like this, and then we have a surface force, which apart from its dependence on position and time, force density. This is again, everything is expressed as integral in continuum mechanics. Momentum is also expressed as an integral. So this is like the momentum density. We have already seen that the units of this will correspond to a momentum density, momentum per unit volume. That is equal to, this is the body force density per unit volume. P is conventionally when it is rho times P. The P represents the body force per unit mass. That's the convention. So we pointed out earlier also that to calculate the body force on this body of fluid, we need to know the body force density at each and every point within the volume to calculate the so-called contact force or the surface force. I prefer the word contact force because surface force means that it's acting on the surface. It's actually not just acting on the surface of the body, it's acting on the body as a whole. It's not really in that sense the surface force, but it's transmitted across the surface. You can regard it like this because to calculate it, you have to specify it on all points of the surface that is enclosing this region of volume in space. To calculate the body force, I need the body force density per volume, let's say rho times P, at every point within the body. But to calculate the contact force, which is again acting, this is the body of interest. But to calculate the contact force on the body exerted by the fluid surrounding the body, you need to specify, this may be regarded as the contact force density. We will call it the stress vector. The contact force density is per unit area. As you can clearly see, because when you integrate over area, you again get the force. Right? So this is the stress vector. Crucial point is it depends not only on the location and time, but also on the normal, outward unit normal, every point on the surface. So that is the statement of the balance of momentum on the body as a whole. Now from this we will get the very famous Cauchy's equation of motion and then see how that can further be integrated to get a statement of momentum, a balance of momentum on a controlled volume, which is what we are probably more familiar. We run out of time, we meet again tomorrow. Take this up.